Okay, so yeah, I should speak in English. All right, so far I think we've covered a fairly large ground of like techniques used in health deep learning for healthcare, or more broadly, machine learning for healthcare. And we only have how many weeks? So we only have, excluding the last week, we only have about 4 or 5 more classes to go. Yeah, okay, so 5 classes, maximum 5 classes, including today's. And so I need to choose my topics very carefully, and not, I think yeah, basic, so yeah, we've only covered the basic techniques, excluding the GAN, the generative adversarial network, that I covered for the last two classes. So it was always the fundamental, like the backbone of machine learning for healthcare was how to dealing with time series data, and we use RNN for it. But I'm not sure if everybody remembers, but briefly when I was talking about processing notes, clinical notes, you could also use, like one-dimensional CNN as well. So one-dimensional CNN is another way to deal with time series data. So it doesn't always have to be RNN. It can be 1D CNN, and even more, we can use transformer actually. So I think it's worth talking about transformer and how it's maybe its place, or an important role that it can play within in the realm of electronic health records. And there is a very deep connection between transformers and graph networks. So maybe we can spend maybe a class or two talking about graph networks and transformers, and how they're actually like very similar, graph networks and GNNs and transformers, and how we can leverage that to actually build, to like propose a more advanced model for handling EHR, electronic health records. And then after, maybe that could take maybe up to 3 classes maybe. So after that, yeah, I'm not sure if talking about more advanced stuff would be very helpful. So we could focus on maybe addressing problems that arise in like projects maybe. But yeah, we'll see. Anyway, so today I'll talk about the transformer, its relationship with graph networks, and its place in electronic health records. Maybe not entirely. Maybe I can't cover the entire topic within a single class today, but I'll try to make it maybe less than three classes. All right, let me just get a cup of water. By the way, is there any specific topic that like anybody's interested in that you would like me to cover? Like any potential topic that you would be interested in? No suggestions, no requests. Okay. All right then. All right, let's get started. So the reason that I'm talking about the graph networks and transformers is that it can be used to build a more advanced model. So these days, so far, yeah, maybe I should talk about the context a little bit. So in the very beginning, I think I'm pretty sure I talked about the structure of EHR, so the structure of electronic health records, and let me just. And how it's all right, yeah. So I've definitely talked about how electronic health records are stored in relational database. So relational database can be seen as a graph, hierarchical graph, if you just lay it out in a lay the entire tables out. So in relational database tables are linked with primary keys and foreign keys, so you can use them as nodes in a graph, so that you can like you can just link everything in a single like very large hierarchical graph. And this is just a subset of the entire graph, where we start with a patient, and then the patient under the patient. So usually in EHR, patients are at the top of the hierarchy. So actually in Mimic3, there are patients table, there's admissions table, there's like diagnosis table. So in Mimic3, admissions table is the one that actually sits at the top. Like if you think about the structure of a relational database, I'm sorry, admissions is the one that is at the very top. So nothing comes into the admission, like, but admission, the admission IDs, basically. So the hospitalization ID, which is HADM_ID in Mimic3. So HADM ID is the one that governs everything in Mimic3. So like what medications were you prescribed, or what diagnosis were you given, or what procedures were you given, or the labs that you've taken, or ICU stays that you've like gone through. Like all these are managed by HADM ID. So in Mimic3, and even the patients. So HADM ID is linked with patient. It's not the other way around. It's not that the patient ID sits at the top and then comes down to HADM ID. It's the admissions ID that sits at the top, and then like semantically, how relational database in Mimic3 is structured is that like there is a admission to the hospital, and this admission was made by a subject. So it's semantically it goes that way. It's not that there is a patient and this patient has made admissions to the hospital. It's not that way. It's the other way. It's that the admission was made by certain subject IDs, certain patients. So semantically in Mimic3, it's not the patients that it's not the patients that everything starts with. It's the admissions table that everything starts with. But if you lay out the entire tables of relational database in a graphical format like this here, it's more natural to start with patient rather than admissions, actually. So if we were to follow exactly the structure of structure of Mimic3, the relational database, then this arrow here should be the other way around semantically, like, because like encounter ID 351 was made by patient ID 523. So that's how Mimic3 tables are set up. But here we're doing it the other way around. Semantically, it's the patient that makes the visit. Like in the real world, the patient is a subject. Patients are the ones that actually make things happen. So it's the patient that sits at the top, and then the patient makes visits over and over again. So like 3 visits here in this figure, and then like under the encounter, there are like diagnosis codes, and then certain diagnosis codes leads to medication orders, like cough and fever leads to medication order ID 15, and just a cough alone makes medication order like ID 345, such and such and such. So this type of this kind of a very complex. Well, it's not super complex, but anyway, it's just like very tightly connected events. Like encounter is an event, and diagnosis codes are events, and the medication order is an event. Procedure orders are events. So these different types of events are intertwined in the EHR. It's not that they just float around. It's not like medication orders are just one group of information, and then procedure orders are another group of information. It's not. It's in reality, it's not that. So that's where the inspiration for using structure of EHR comes from. So previously, yeah. So this is if you just simplify it. So Actually, yeah, if you guys already like looked through the tables of mimicry, so you know that there are a lot of information, like 25 tables, but if you simplify everything, then you can just dumb it down like this. So there's like a sequence of visits, and then under the visit there's a diagnosis codes, and then under diagnosis codes there are treatments like medications or procedures, and then some procedures usually leads to lab measures. So like if you take EKGs, or if you take blood samples or urine samples, like those kind of like procedure orders usually lead to lab tests, and then like after lab tests you have lab results. So sometimes under the procedure there are lab results. So you can see there's like a hierarchy of things, and this kind of information, this like things happening in order, it does contain a valuable information, because this reflects the physician's decision process. Because in like if you like when the patient visits the hospital, then the diagnosis is made by the physician. So physician talks with the patient, like has a conversation, like what's your problem, or do you have any complaints, or do you have any pain or something like that. Like there's like a short amount of conversation going on, and then doctor makes a diagnosis, and then types that into the report, and then depending on which diagnosis the patient has or the patient was given, the doctor makes a appropriate medication orders or procedure orders. Sometimes it's the other way around. Sometimes the doctor is not really sure what the diagnosis should be for the patient, so he or she like orders a procedure, like some tests to identify what kind of problem the patient has. But like in overall, generally speaking, there's always a tight connection between the set of diagnosis codes and the procedure or medication orders that comes after or before. I mean, medication order will always come after. But anyway, so yeah, this kind of captures a single visit to the hospital, and this is specifically a outpatient visit. So the outpatient 외래 환자. So there's no like. So if we talk about inpatient visits, then the graph would be way more complex. So yeah, I'm talking about 입원 환자 and 외래 환자. So 입원 환자 is the inpatient, 외래 환자 is outpatient. So inpatient, they stay at the hospital for several days. So this kind of like a snapshot cannot happen. But that's another topic. So the motivation is that so far, how I've talked about processing EHR, and how probably everybody has processed EHR when they were doing assignment number 3, is to, so when something happens at the same time in visit, like, well, I guess not exactly, because so far we've only dealt with ICU stays, and in the ICU stay itself is a single visit. So I guess I guess nobody has actually like come upon this, encountered this problem. But okay, so the problems that we've dealt with so far were always using inpatient data. So that's kind of it's an unfortunate event, unfortunate incidents, because the only open source, like publicly available EHR datasets are all inpatient datasets, EICUs or Mimic3, or there are a couple more like open source EHR datasets. They are all ICU datasets, but usually there are way more outpatient encounters compared to inpatient encounters in the world. I mean, obviously, you don't usually get like you don't usually stay in the hospital for several days unless you're like unless there's something significantly wrong with you, right? So if you just go through the electronic health records of any hospital, any large hospital, outpatient records are way more frequent, like way large, like the volume of the outpatient records is way larger than the volume of inpatient records. So usually people have more like use for machine learning techniques when they want to model so the purpose is usually to model outpatient records rather than inpatient records. If we talk about like longitudinal electronic health records, or if we want to model like chronic disease, like like kidney, diabetes or hypertension, or like, you know, like some of those like chronic diseases, they progress over a certain number of, like, over years of time, not just like several days, like over years of time they progress. They, like, you know, patients develop them and then they become ill. So so like, the compared to that, what we did with the assignments in using ICU dataset, they usually happen over like several days maximum. Except, and even like the most, even like, even in assignment number 3, we cut down. We've only filled, we've removed all the patient records that that's where the ICU stays happened more than 2 days. We only took the ones that happened like between 24 hours and 48 hours. Like, so it's a very short, like, period of time. So within that time frame, you don't usually model like chronic diseases like hypertension or diabetes, like how they change over like 28 hours, 24 hours, or 48 hours. You never do that. Like, within 24 or 48 hours, you usually model acute diseases like 급성 신장염 or 급성 신부전, something like that, like acute kidney failure or acute heart failure, acute whatever. Like, that's the kind of thing that you want to model when you are dealing with ICU data. When you have outpatient data, you want to deal with something that like, you know, spans over like at least several years of time. So, and so this whole so the motivation, like, this snapshot, and also the visit that I'm talking about, this is all like we're talking about in the context of outpatient records, actually. So yeah, it is quite unfortunate that we don't actually get a chance to, I mean, like, when we say we, I'm talking about the students, like attendance of this, I mean attendees of this class. Like, we don't have a great chance. We don't virtually, there's no chance that we can get our hands on any publicly available outpatient records, because there is no such thing. So if someone is really interested in, like, you know, processing outpatient records and modeling chronic diseases or like long-term diseases, the only way they can do it is to, in Korea, probably talk to like hospital people, like as like Seoul National University hospitals or Asan Medical Centers or Samsung Medical Centers, like large hospitals. They have like millions of outpatient records. So that's the only way, unfortunately. Anyway, so but still, like, generally speaking, it's like way more a popular topic in machine learning for healthcare. So yeah, well, I'm gonna address one specific problem when one specific problem that everybody had so far when dealing with outpatient records. So all right, so enough background. All right. So in outpatient records, what we do is we usually take one visit at a time, because the patient goes to hospital and then that's it. Like, there's no admission. The patient doesn't stay in the hospital for like several days. So the patient goes to hospital, gets diagnosed, get prescription, and then leave. And that's the end of the interaction as far as that's how interaction goes. It's just a snapshot. That everything just happens in like several hours, not even several hours, maybe like 1 hour, 2 hours. 1 hour, 2 hours. So you can view a single visit as a snapshot. Like, just there's no flow of time within a single visit. So what you usually do is you take a visit by visit and then push that into the RNN. Or it could be any sequence model for that matter. It could be any sequence model, but it's usually RNNs are the most robust model. So how you would handle outpatient records is you take one visit at a time, and then you want to like feed one visit to the RNN, and then move on to the next visit, and then feed that to the RNN, and then move on to the next visit and feed that to RNN, like, you know, repeatedly. So it's a sequence of visits, and within a visit, there are a lot of things happening within a visit, because as you can see, like, this is a single visit here, like maybe 4 or 5 diagnosis codes, and then maybe some medication orders, some procedure orders, and maybe some of them leads to lab measures. So this is a single outpatient records. And so far, what we did when we had, like, I don't know, 1, 2, 3, like, there are 1, 2, 3, 4, 5, 6, 9, like 12. There are 12 events within the within the teeth visit. So if we had, and here in this diagram, there are 4 events in the visit. So like, for example, let's say that the patient went to the hospital and then got diagnosed with cough and fever, and then the medication was given, which is Tylenol, and then the patient was given the procedure of getting IV fluid, like SWIC or some fluid into intravenously. So 4 events, and naturally, what people did so far, starting from like 2015 to all the way to maybe 2018, 2019, is a single visit can be represented. I mean, we still want to represent a single visit as a vector so that you can you can feed them into the RNN. So the usual way, like everything is a vector in deep learning. So what you would do is you represent a single visit as a fixed size vector. That's necessary. In order to feed a single visit to the RNN, you need to convert a single visit to a fixed size vector. And how people did that is they just summed everything up. So there's a vector or representation vector for cough, and there's like the embedding. I mean, embeddings and representation vectors are the same thing. So there's cough embedding, there's fever embedding, there's Tylenol embedding, there's IV fluid embedding. So there are embeddings or representation vectors for each event within a visit. So naturally, what people did is they just summed those vectors up, those embeddings up, and then that became their visit representation for visit 1. And I mean, you don't have to like you don't always have to sum them up. You can just average them, or maybe if you're clever, then you want to use like attention mechanism on top of it. So you don't just simply add them up. You have like attention function that sits on top, so that like you get a convex combination of these 4 events. But still, basically, you're adding them up, and by adding them up, what you're doing is virtually. I'm gonna skip this. This is another way to add embeddings up. So virtually, when you are just simply adding them up, you're just flattening the structure and losing the information, the hierarchical information within the visit. So like if you like simply just treating cough and fever, Tylenol, IV fluid, all those different events as equal type of information, and then adding them up like this, is you're virtually destroying this hierarchical information, because within the visit there's like diagnosis level, and there's like medication order level, there's procedure order level, and then there's the lab result level. So, and then they have interaction with each other, like these red arrows here, the red arrows here, like these red arrows, they indicate why they were given and why certain things were ordered. And that reflects the physician's thought process, like, oh, because of fever, I'm gonna give this patient an IV fluid, which is completely different from, oh, this patient has chest pain, so I'm gonna give them IV fluid. Like that kind of thing rarely happens, but still, like if there are a lot of codes, a lot of events happening within a single visit, then this kind of like relational information, these red arrows, play a huge role, because as a single visit contains more information, more events, then there are like the number of cases, hypothetical cases that you have to consider becomes exponentially large. So if you actually narrow them down, if you just like narrow your hypothesis space down by giving this red arrow information explicitly, you're actually making the model's life way easier. But if you don't, then all burden, if you just simply add them up, then all burden falls on the RNN to understand what happened in a visit. So here, there's only 4 events, so it's pretty obvious, like cough and fever led to Tylenol and IV fluid. But if there were like more number of diagnoses, if there were more prescription, more medications, and if there were more procedures, then like the RNN, which receives the visit, has to figure out what exactly happened within the visit. So so that's the motivation for that. We can say that that's the motivation for actually wanting to preserve the hierarchical or graphical information within the visit when you model like outpatient records. So it's not, and the same principle can be applied to inpatient records, because inpatient records, there's certain like relationship between like medications, procedures, and labs, and even like medical notes and diagnosis codes. Like they all are interconnected in a specific manner. They just don't happen over time, and they like in a bag of feature. Like here, this is called bag of feature approach, or bag of codes approach, because there is no sequence among them. There is no relationship among them. Everything is just equal parts. So it just is like they're in a bag. So here the bag is the visit. So they're in a bag, which is called the visit one, and then everything is just within the bag. Everything is just the same. So this kind of like bag of features or bag of codes approach doesn't really help. So, and as I was saying, the same principle applies to inpatient records, like Mimic3 ICU stays data, because when things happen, the time-stamped events, they happen over time, even within a single visit. Like things happen over time because the patient like stays in the hospital for like several days. So, but even so, you can think of them. You can think of those like events that happen over time as an evolving graph. Like here it's just this this is a static graph within a single outpatient record. This graph doesn't change. Like once the patient goes to the hospital and then leaves, this graph stays the same like forever. But within like an inpatient record, like ICU stays, there like some diagnosis is given and then some medication codes is given and it's removed, and then some procedure codes is given and then it's received and then it is removed. Like things like come and go within the like several days of time frame. So it's an evolving graph, and which is way harder to model compared to static graphs. So yeah, there are some relevant works that is purely theoretical. I haven't seen like model it. I haven't seen as of yet so far. I haven't seen works that model ICU stay records as an evolving graph, but surely someone will do it like sooner or later. Anyway, so I guess let me see what's the best approach of talking about transformer first or graphical neural networks first. Actually, so let's talk about this approach a little bit more, so that it is a bit more clear. I guess today we can talk about this, how we can approach this, how we can solve this problem. Like when we used to flatten everything. So when we used to flatten everything like this, and compared to that, this new approach called MIME, which is another model that I proposed and was presented in NIPS 2018. So this is very, very similar to graphical neural networks in retrospect, but I guess, so this is all hypothetical so far. So far, flattening the structure is not good for the model. It's bad for performance, not an optimal approach. This is all hypothesis. Intuitively it makes sense. Intuitively, it's good motivation, but before empirically showing that this hypothesis is a legitimate hypothesis, and this motivation is like it's a well-motivated problem, we need to empirically show it. So let me just show it. Let me just spend some time to show that actually this kind of thing really is helpful. So, and why a lot of people these days are interested in applying graphical neural networks on top of electronic health records these days. Like I'm seeing more papers that tries to combine electronic health records with graphical neural networks, or I haven't seen a lot of works that combine transformers with transformers with electronic health records. But as I'm going to say, as I said, they are actually the same. Transformer and graph neural networks are just the same. It comes from a same family of model, or same family of like functional space. So anyway, so that's another, maybe I can talk about it in the next class. Anyway, so to empirically show that this hypothesis stands, what I did is I proposed, so I dumbed it down a little bit more. So this is there's the visit level, there's diagnosis level, and there's treatment level. I haven't dealt with lab measures in this project, but it's a trivial manner to add more add more things, add more events below the treatment level. There should be like a lab level, but this is a bit more simplified. Anyway, so in order to capture the interaction, in order to capture the relationship between the treatments and diagnosis, what I did is I came up with a concept called diagnosis object. So there's like here in this fatigue diagnosis code, it doesn't lead to anything. It's like, you know, fatigue didn't lead to any like medications or procedures. So fatigue itself becomes a single diagnosis object 1, and cough leads to benzonatate and acetaminophen. So those 2 are medications. So cough leads to ordering 2 medications. So like as a set, like here, the cough and benzonatate and acetaminophen becomes diagnosis object 2, and then repeatedly, like fever and acetaminophen and IV fluid becomes like object number 3 and object number 4 and object number 5. So what I'm trying to do is I'm trying to explicitly capture the relationship between the treatments and the diagnosis that led to those treatments. So that is why I'm introducing this thing called diagnosis object. And so before, a visit was just a set of individual medical events, like codes. And sorry. So yeah, okay, I'm sorry, there was an interruption. So before, a single visit was a set of unordered set of codes, like diagnosis and medication procedure codes. It was just a bag of codes. But now, visit can be seen as a set of diagnosis objects, because here there were how many diagnoses? There were 1, 2, 3, 4, 5 diagnosis objects. So a visit is a set of diagnosis objects. So it's a combination of diagnosis objects. So, and within the diagnosis object, there's there's a diagnosis code, and there's a following procedure or medication code. So a single diagnosis object consists of a main character diagnosis and the following treatments. So I won't go into detail about the mathematical operations, but basically it's just a top-down, no, it's a bottom-up approach. So this red box here is a diagnosis object, and then diagnosis object so usually what we're interested in the outpatient record is given H, which is a patient embedding. So H is a patient representation vector, and Y is some disease, some event that we want to predict, like heart failure or kidney disease or hypertension or COPD. COPD is what? It's some pulmonary, some lung related disease. Anyway, so those are the typical chronic diseases that progress over time, that develops over like years of time. So given patient records of like several years, outpatient records of several years, we want to predict whether some patient will develop like chronic disease like within like next year maybe, or next month, or maybe, you know, in the next 6 months, some given time frame. So Y is the label, H is the patient embedding. So so H being the patient embedding, then there should be patient representation vector. So patient representation vector, and the patient is a sequence of visits, because the patient makes sequence of visits. So there's the patient level, then there's visit level, because like there's visit 1, visit 2, visit 3. So there's like individual visits form a sequence of visits, and then within the visit there's diagnosis objects. As I said, there's a set of diagnosis objects. So diagnosis object 1, 2, 3, and then within the diagnosis object there's the main character diagnosis code D, and then there's the set of treatments that is led by the diagnosis. So it's a very, very hierarchical approach. So like there's patient, there's visit, there's diagnosis object, there's diagnosis, there's procedure, and there's treatments at the bottom. So you start with the treatments to roll up these embeddings up to the very top, to the H. So in the bottom there's treatment embedding, there's medication embeddings, there's procedure embeddings. So at the very bottom there's embeddings for the treatments, and then you roll it up like repeatedly. You roll up to the diagnosis, and then you roll to the diagnosis object, and then you roll it up to the visit, and then maybe you want to push the sequence of visits to the RNN, and then you get the H, and then you make the final prediction. So there's a lot of levels here. So that's why it's called multi-level embedding. MIME is a short for multi-level embedding. Anyway, so yeah, I'll just skip all the details for the mathematical. And yeah, formula. Yeah, I'll just skip the formulation. Yeah, it doesn't really matter because MIME is a very specific. In retrospect, MIME is a very specific case of, or special case of graph neural networks. So it's better to talk about graph neural networks than talk about MIME to mathematical formulation. So, I mean, we'll do that maybe next time. So graph neural networks mathematical formulation is better. And of course, we're gonna talk about transformers self-attention mathematical formulation and how they're actually very similar to each other. So before we do that, let me just finish the motivation part of MIME and how empirically it's better to capture the relationship between, like, hierarchical relationship between the codes. It's way better than just flattening everything. All right. All right, so the experiment setup is, yeah, I think I've talked about the Sutter Health data set a couple times already. So it's the same setup. So Sutter Health, the healthcare network in Northern California, they gave me about outpatient records of about approximately 30,000 patients, and the number of visits is way large. And I mean, like, you can divide. So the total number of outpatient visits was about 600,000. 600, to be more specific, is 616,000 outpatient records. And if you divide that by the number of patients, then you can see that on average, patients over 18 months of time, that's about a year and a half, over 18 months of time, each patient made on average 20 outpatient visits to the hospital. So within like 18 months. Seems reasonable, right? Because people usually go to hospital maybe, I don't know, maybe once a month. And they are, no, not, that's a bit more than usual. So these are all senior patients, patients between the age of 50 and I think it was 85 or something. So like senior patients are they're more likely to go visit the hospital than like young people, like younger people. So 20 times over 18 months period of time is not unreasonable, I guess. And the number of features, number of codes within this data set is about 2,300. So among like about 400 diagnosis codes, 100 medication codes, and about 2,000 procedure codes. And they are grouped actually. So I grouped the full ICD-9 codes into like about 400 categories, and like I don't know, 20,000 different medication codes into about 100 higher level concepts, such and such and such. So it's a bit dumbed down actually. And so because the hypothesis was that flattening the structure of visit structure is bad for your model. That was the hypothesis. So the baseline should be various ways to model individual visits, but in a flattening manner. So there's like linear embedding where you just simply add the embedding vectors of codes, and nonlinear embedding is you add them up and then you push them through a nonlinear activation function, like sigmoid or tanh for value. So that's the only difference between linear embedding, nonlinear embedding. And the third one is just putting more layers, so increasing the power to model the visit to model a single visit, because theoretically speaking, if you add more hidden layers on top of like nonlinear embedding, theoretically it is powerful enough to capture all kinds of set information. I mean, so theoretically this should be as powerful as the model that I'm proposing, MIME, because it is as expressive as MIME. Like there's like a theorem called universal approximation function, which is that if you have like certain number of hidden layers in your feed forward neural networks, then your model is powerful enough to model any type of functions, like potentially anything you can think of, it can model. But in reality, it's never the case because it's all theoretical. But theoretically, it is proven. So anyway, and then there are two more prior works of mine, which is Medvedev and Graham, but they're clever approaches to modeling a single visit, but they are still using flattening structure. So okay, so five baselines. compared to that, MIME here, this MIME here and here, this is the one that actually doesn't flatten the approach, the one that uses the diagnosis object, the new concept. So this is a heart failure. So given the first, I did a lot of experiments to show that empirically the hypothesis of, the hypothesis where the flattening the structure is bad for your model. In order to show that, I did a bunch of experiments. So experiment 1 is heart failure prediction. So given the 18 months record of 18-month record of 30,000 patients, given that, trying to predict whether each patient will have or not have heart failure diagnosis within the next 1 year time window. So, and if you think about here, if you think about explicitly providing this red arrow information, this like which treatments are connected to which diagnosis codes, providing this information to the model is actually quite like, I think it is equivalent to regularizing the model. So by explicitly giving this information, compared to just adding everything up, compared to just adding everything up and then giving this information to the model, explicitly explaining this kind of relationship exists to the model is equivalent to regularizing the model's hypothesis space. So before, if you give like this, then anything could happen. Like if you just add these up and then give to the model, I'm sorry, excuse me, then any relationship is possible. So there are like, I don't know, 2 raised to the power of like 12 number of relationships possible. So the model needs to consider all possible combination of relationship when it is trying to predict something, like predict heart failure. But if you explicitly give this information to the model, then the model doesn't need to figure out or try to imagine what kind of relationship the codes have with each other. So by regularizing the model, or like just narrowing down the hypothesis space of the model, we're making the model's life easier, actually. I'm sorry, something, am I hearing? I'm sorry, there was an external noise. So anyway, so because this is equivalent to regularization, then naturally you want to test it on a smaller data volume, because regularization is usually, I mean, most common reason for using regularization is because you don't have a lot of data, but your model is like too expressive. So you don't want your model to learn like nitty gritty every single details of individual, like every single details of the data set, like memorizing. Like you want your model to learn the pattern, not the specific corner cases of your data set. So regularization is usually used when you have like smaller number of data set, smaller volume of data sets. So so what I did is exactly along that line. So there's a training set and there's test set. So by fixing the test set, I'm only adjusting the size of the training set. So the lower the volume, or the smaller number of training set that I use, then the more effect that I'll see coming from the regularization. So you can see that the MIME model always outperforms other models. Like there's a lot of lines here below, but so which are the baselines that just flattens the structure, flattens the visit structure. So compared to that, MIME always outperforms them, but it especially outperforms them when you use a smaller number of data sets. So compared to here or here, when you like use like 20,000 or 27,000 patient records, using 15,000 or 6,000, MIME shows like better, the gap is wider basically. So this is a PRAUC score. So the gap is wider when it is using less number of samples. So because, as I said, MIME is basically a very specific way to regularize it's a very specific regularization technique or regularization strategy. So this is one way of viewing and one way of empirically showing. Another is, as I said, this kind of like regularization or giving this red arrow information is especially giving this red arrow information is especially effective when there are a lot of things happening within the visit. For example, if there's only 4 things happening in the visit, then it's pretty obvious, like there's not a lot of things to things like you don't need a lot of imagination or you don't need to wonder what's the relationship between like each individual codes, because obviously cough and fever led to Tylenol and IV fluid. So, and even more extremely, if you just have one code in visit 1, just like one thing, just cough and that's it. Like you had a cough and then you just left the hospital. Like the doctor said, oh, you have a cough and you don't need to worry about it. Just go home and just take a rest. Then one code happening in the visit, then you don't need to bother with this kind of like this complex hierarchical graphical structure. You don't need to bother with that. So MIME is only effective as long as you have this kind of like complexly structured visit. Like if you have like very simple structure, MIME wouldn't really be very helpful, obviously. So this next set of experiment is exactly exploring that area. So D1 and D2 and D3 have D1 has the simplest visit structure, and D3 has the most complex visit structure. So, and I bucketed them so that they have like about the same number of same number of patient records. Like about 55,000 here, about 5,000 here, about 5,200 here. So about more or less, give or take, about the same. And here I'm using a concept called visit complexity, but you can think of them as just basically how many treatments are given per diagnosis codes. Because if you don't like, if there's even if there are a lot of codes, even if there are a lot of diagnosis codes, if you just have one single medication codes or one single treatment codes, then you don't have. No, I'm sorry. It's the other way around. If you have like a lot of treatment codes, like a lot of medications or procedure codes, but if you have just one diagnosis code, then you don't need to wonder about the relationship. It's that one diagnosis code that led to all the medications, all the procedures. So in order for the model to be confused when flattening the structure, it needs to be the other way around. It needs to be that there are a lot of diagnosis codes, and there are a few number of treatment codes. So you don't really, if you just flatten the structure, then you don't know which led to which. So that visit complexity is basically a proxy for measuring that. So D3 is the most complex, D1 is the most simple. And you can see that in the simplest case in D1, there's not a lot of gap between MIME and the baselines when it comes to PRAUC. So you can see like even like 10H or Metovec or 10H with more hidden layers, you can see that 27% PRAUC is the same. MIME, even like MIME vanilla and MIME Ox is a bit more advanced, but you can think of them as the same MIME. So MIME has like between 26 and 27% PRAUC. You can see the same, like 27, 26, 27 here. So it's the same. But if you go to D3, which is the most complexly structured visit, we're dealing with like most complex visits, then you can see that MIME has about 47%, about 47, 48%, 46, 47% APRAC. Compared to that, the next best thing is 44% 10H. And all the others show like 38, 39%, 43%. So the gap is way wider compared to D1. So as I said, D1, there's nothing to be confused. There's no benefit from moving from flattened structure to hierarchical structure. You don't get a lot of benefit when you're dealing with simply structured data visits, but you only see the effect or the benefit when you move on to the complexly structured visits. So yeah, I guess the takeaway message is if your patient is a very simple structured outpatient records, then this kind of whole motivation doesn't really apply. But usually there are always Like even when you, especially when you go to senior patients are usually very sick. Like there are, if you get old, you usually have like 1 or 2 chronic diseases, and you always have like joint pains and skin disorders, and like, you know, like basically your body function degrades. So a lot of things happen to you when you go to the hospital. You get a lot of diagnosis, you get a lot of medications, procedures. So when you're dealing with senior patients, this kind of approach, like this MIME approach, should be really helpful. This is another thing. So this is another thing. So far here, this one and this one was heart failure prediction. And this is another thing. So as I said, I did a like extensive experiment to show that this hypothesis is this motivation is a like well motivated problem, in order to show that this is another prediction problem. So this is not heart failure prediction. This is sequential diagnosis prediction. And as I said, a patient can be seen as a sequence of visits. So up to like up to teeth visit, you can gather the data and then try to predict what would happen in the T+1 visit in the next time, right? You can try to predict what kind of diagnosis the patient will have when the patient visits the hospital next time, and then the next time, and then the next time, like repeatedly. So sequential diagnosis prediction that is what sequential diagnosis prediction is doing, repeatedly predicting the set of diagnosis codes. And as I said, regularization technique is good for small data volume. So small data volume can be achieved, can be seen by explicitly, you know, removing the training data set. But so like having absolutely having smaller data set is one way to see as like one way to view as like a small data volume. But another way to view, another way we encounter small data volume is when we deal with rare diseases. As I said, I think I've covered this in the Graham paper. So rare diseases is another way to is another like a form of like low data volume. So even if you have like tons and tons of data set, tons of like patient records in your hospital, but if you're dealing with very rare diseases or like hereditary disease, genetic diseases, then you don't see a lot of cases to begin with. So it doesn't matter how much like total data set you have, because if you focus on a specific rare disease, you never have enough amount of data. So here, what I'm doing is, as I said, I'm trying to predict the diagnosis codes. So I I've categorized the diagnosis codes into like the most rare, like this is the most rare bucket. This is a bit less rare. This is a bit more common. This is the most frequent. So like hypertension, you probably sits in here. Like it's the most frequent disease among the senior patients. And I guess, I don't know, like genetic diseases or like things that happen usually to like children should sit in here when it comes to like when you're dealing with senior patients. So the hypothesis is the same. It's still the same principle. Because MIME is a regularization technique, it should outperform other models when it is dealing with rare diseases. So, and it empirically it shows. So here, actually, this is a bit of an exceptional case. When we're dealing with truly rare diseases, things that have like only a 0.01% prevalence rate. So that means like only out of, I don't know, out of like out of 10,000, is it 10,000? 1% is 100. Yeah, out of 10,000 patients, only one of them have this disease. So this is truly rare disease. So in this bucket, like of course everything shows like very poor performance, but Med2Vec, it outshines all the others. So this is like the exceptional cases where we're dealing with really rare diseases. So I guess there's not a really good explanation why Med2Vec outperforms Graham or MIME. But if you move on to the next bucket and the next bucket, then you can see that the performance gap between MIME and the baseline is wider. So it's 26% PRAC here. No, I'm sorry, this is not PRAC. This is accuracy at 5. So anyway, so this is 26% accuracy at 5 here compared to 23 so it's the gap is wider compared to like 44.47 and 44 here. Like this is 44%, this is 44%. So if you have a lot of like, if you're dealing with really, really frequent disease like hypertension, then there's no like, you know, pure like clear benefit by using advanced models such as MIME. You're fine with using just flattening the structure, and you can still like get by. Like this is as good as 44%. This is as good as 44%. But if you like, you know, if you come back to the rare diseases or rarer diseases, then the gap is wider. This is like 36%, 34%, 26% to 23%. So you can see that there's a clear like benefit from leveraging the structure of EHR. Right, so the conclusion is that the EHR structure reflects the physician's decision process. So as I said, yeah, the explicitly showing the relationship between diagnosis and is leading procedures or medication. And of course, if you can add more stuff like labs that come out of the procedures or notes that come out of certain like, you know, certain visits, you can all model them in a graphical, you can all view them in a graphical manner and try to use one way or another graph neural networks to, you know, to inject the physician's like, you know, domain knowledge into the model. And so that does improve prediction performance. And, you know, obviously you can extend this approach to including more modalities. So that is okay. So this was kind of a very like a long motivation for the motivation to treat the, I guess, yeah, as to why the structure of EHR is important, basically. All right, so moving on to the next one. So what the reason that I'm talking about the relationship between the graph neural networks and transformer is because we don't have a lot of time today. So okay, I guess I can just give the motivation and then talk about the technical detail next time. Right here. So okay, so in MIME, without actually realizing, what I was doing is I was actually implementing a very special case of graph neural networks. But if anybody's already familiar with GNNs, graph neural networks, or, you know, graph convolutional neural networks or graph attention networks, you can readily see why it is a good idea to why graph neural networks are such a natural fit to electronic health records, because there is a graphical structure here. So you can just convert this graph, starting with visit node. So there's visit node, there's diagnosis node, there's medication and procedure nodes, and there's lab nodes. So this graph consists of 13 nodes, and you can convert this 13 graph of 13 nodes into adjacency matrix by, you know, you can very easily construct a adjacency matrix where like cough is connected to acetaminophen and benzonatate, fever is connected to acetaminophen and IV fluid, and so on and so forth. So it's because there are 13 nodes, you will have a adjacency matrix 13 by 13 rows, like 13 rows and 13 columns, and you can like construct a binary adjacency matrix, and then you can use that as a adjacency matrix in graph neural networks to, you know, to learn the embeddings of individual codes, or maybe the whole graph itself. So that is why it's such a, like, graph neural networks are such a nice natural fit to modeling EHR. But sometimes these red arrows are not always available. So sometimes the hospital is just, you know, they just don't store that kind of information, because hospital by hospital, they use different, they always use relational database to store EHR, but they always use different schemas. So the structure of the tables is all different, hospital by hospital. So some hospital does store this red arrow information, like why certain medication was ordered and why certain procedure was ordered. Like they record that information and then store that into the relational database. But some hospitals, or I guess I would say majority of the hospitals, don't store that information. They just store information like what medication was ordered in which admission, or which outpatient encounter, and which diagnosis was given in which outpatient encounter. Like it's all like they're independently treated. The relationship between the procedure, the diagnosis, and the treatments are not explicitly recorded in their relational database, which is unfortunate, and which is the case for MIMIC3. In MIMIC3, there's no reason field, like medication orders and procedure orders. There's no reason field in MIMIC3, and which is the same in EICU. So, and of course, it's the same in claims data. Claims data, there's no claims data is usually for like getting reimbursement from the government insurance policy. So you don't need to record why certain things were ordered. You just list the things that you did, the services that you provided to the patient, and then you just get reimbursed. So a lot of EHR data that you can get your hands on in the real world, they don't contain this red arrow information, which is unfortunate. So in that case, when the red arrows are not available, in that case, you can't actually use graph neural networks, because you cannot construct the adjacency matrix for this teeth visit. So the motivation, the connection between the transformer and the graph neural networks comes in to overcome, to remedy this situation where you cannot use graph neural networks. So graph neural networks, you can use them when you explicitly know the adjacency matrix. Transformer can be a solution when you cannot construct the adjacency matrix, or when you can only partially construct the adjacency matrix. All right, I guess we can end a little early, because we need to dive into the mathematical formulation of transformer and graph neural networks. So that's gonna take some time, actually. To be honest, I'm not sure if I can finish that within the next class, actually. So all right. All right, okay, I'm gonna end the class today here, and we'll revisit this topic next Tuesday. So any questions so far, like the graphical nature of EHR and the MIME, the project, the MIME architecture, the model that I explained today? Anything generally, or even with regard to the projects, like any challenges or barriers that you might have? Like, if you have any question, I'll stick around for a couple minutes. If not, I'll see you guys next Tuesday. Thank you. Thanks guys, and have a good weekend.